Good evening, hackers. Welcome to Chill Code. My name is Taggart, and once again, I have forgotten to update the subject Chiron. There we go. That is what we are up to tonight. We are doing some code challenges in Haskell. In particular, we're going to do some advent of code. We'll see how far I get. These are usually kind of involved, and fair warning, I may just get like bored of them, but we'll give it a shot. I really want to give it a good college try. And yeah, by popular demand, or at least vocal demand, we're going to try these in Haskell, everybody's favorite language to complain about, basically. I love Haskell. There's a lot to like about it, and admittedly, I'm a little rusty on it, so I'm looking forward to getting my functional chops back with these challenges. If you want to play along, I want to talk a little bit first about how you set up Haskell for success in your environment. Now, you can do this in Windows, but if you can at all avoid it, I would recommend not doing it in Windows, just because it's a little bit annoying. Totally doable, but I do find that on the Linux side, things tend to go a little bit better. So if you can do this in WSL, if you're on Windows, definitely the way to go. So the first place you want to go is the get haskellstack.org, basically. And what that will do, you can kind of follow the instructions here to set up everything. And this is, there's a tool called Stack, which is, think of it as Haskell's package management, and think of it as Haskell's cargo or Nimble for Nim, if you're used to what we've been doing with Nim. That's what Stack is, and it has the ability to set up template folders, things like that, and it's the easiest way to install everything that you need to do Haskell. You can do the components manually if you want. You can install the GHC or the Glasgow Haskell compiler if you want. You can do it that way, but I just find this is super easy. So if you want to get that going, once you have that set up, you should have a couple of different command line tools. You should have Stack, you should have GHC, and you should have GHCI. All of those should be available to you. And I'm actually not going to use Stack tonight if I can get away with it. Giant Kumarak, thank you so much for the follow, and thank you for your kind words during the talk today. Really appreciate it. So that's how you get Haskell set up, and then I'm using VS Code, of course, as my editor. It has really good Haskell support. But I am going to use Haskell I'm going to use VS Code in conjunction with my WSL terminal here. You see I have it split top and bottom. Top is going to be kind of my scratch pad. I might use a text editor in there. I might do command lines. And then in the bottom, I'm going to have the GHCI, the interactive component of the Glasgow Haskell compiler running. Why? Because it's really handy to test things out as you go, and to investigate parts of the language. I find the GHCI to be basically a requisite part of Haskell development. So we're going to have that running in one of our windows as well. And this is similar to the pattern that I liked. I basically don't use IDEs for any language. I'll kind of cobble together the tool set that I want between my text editor and then any terminal stuff that I think is necessary. That's the way that I tend to work, even for things that I could do in an IDE like C#. Not that I do a lot of C#, but I basically don't pay for IDEs is the thing. Okay, so let's take a look at challenge 1 here and see what's up. And if you've done this one, great, but I'm starting from scratch. I haven't done any of the advent of code yet. So you're minding your own business on a ship at sea when the overboard alarm goes off, blah, 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 blah. So if I understand it correctly, what we're doing tonight is you're in a submarine. As the submarine drops below the surface of the ocean, it automatically performs a sonar sweep of the nearby sea floor. On a small screen, the sonar sweep report, your puzzle input, appears. Each line is a measurement of the seafloor depth as the sweep looks further and further away from the submarine. So the trick is to figure out how quickly the depth increases, just so you know what you're dealing with. To do this, count the number of times a depth measurement increases from the previous measurement. There is no measurement from the first measurement. In the example above, the changes are as follows. So, no previous measurement, so there's no increase. The next one, because the previous was lower, that's an increase. The next one, the previous was lower, that's an increase. So we're counting increases here. Interesting. So if you think about this and then the answer is how many measurements are larger than the previous measurement, and we have the input here. It's big-ish, a couple hundred lines maybe. I have saved it to input.txt here. How large is it? 2,000 lines. Okay. So what do you want to do with this? If you are thinking about this in a traditional programming context, you might think, okay, load up the numbers from the text file, turn them into numbers, and then do a for loop and just like see if it's if the previous index is less than the current index, then we count it, right? Here's the thing with Haskell, we don't have any for loops. There are no for loops in Haskell. So we have to think a little bit differently about how we order our code, because that is not how the language works. It is a functional language, not an oh god, what's the word I want? Imperative language. We are not creating a set of instructions. We are creating a set of transformations of data. And I know that might seem a little bit different, but basically we have to create a flow of functions from one to the next, where we have our starting point, and then by the end of our function flow, the data has to be in the right shape for what we want. And that difference in approach is what makes Haskell a challenge for new programmers, and functional languages in general a challenge for new programmers, but also what makes it so powerful as a way of thinking as a programmer once you master it. Is that similar to the way that Lisp works? Yes, it is. Lisp and COBOL, of course, or Fortran were kind of like the original two branches of programming. And Fortran was the declarative imperative language, and Lisp, the original Lisp, was functional. And they kind of just went their two separate ways. So very similar to how Lisp works, where you have enclosures of functions upon functions with those parentheses that are so infamous. But yes, now modern Lisps, I will say, have like helpful things in them. I might have to change up the tunes here. It's too jazzy. Let's turn that down a little. Modern Lisps have helpers for that. So for example, in Clojure, which is the JVM, the Java Lisp, there actually is a for loop, believe it or not. So they actually have these helpers that make it a little bit easier. I think Racket has a for as well, or at least a loop, where you can kind of do that. There are those parentheses. So it's a little bit of a helping hand there. Whereas Haskell is a pure functional language. It does not mess around with any of that at all. So we have to come up with another way of thinking about that. And generally, in a functional language, when you're thinking about iterating through something, you either are dealing with something that could be described as a fold, or a map, but a fold is the general case, or a recursion. And we'll see which one of these we are closer to here. One of those two is going to be closer to what you want to do than a traditional for loop. So in our case, let's actually use our scratchpad here. One of the things, again, I like about Haskell, I don't need VirtualBox open, is we want to plan. So we're just going to open up a text file here, and we think about what is it that we're bringing in. Well, we're bringing in, basically, we'll start with an array of strings. Ooh, you've never heard of a fold. Okay, stop the presses. A fold is a really important concept in functional programming, but you have it in other languages. You have it in Python and you have it in JavaScript. So a fold is, we'll bring up fold L in Hugel. Although the definition of it isn't going to be super clear without using it. Yeah, if you don't know how to read Haskell function definitions, this doesn't make any sense. But let's think about what a fold does in general. A fold takes three things. It requires three things. One, it takes a starting point, what we call an accumulator, which can either be set to an empty list or an empty array, or 0 or an empty string, whatever it is, a starting point called an accumulator that you're going to change. Then it takes a list of things to work over, whether it be an array or a string, something iterable. Okay? Then it takes a predicate, a function that you're going to apply. Now that function is special. It's a little bit different than like a for each or something like that. That function takes two arguments. The first argument is the accumulator itself, which you pass into the function and get to modify every time you apply that function to elements in that iterable. Then the second is the current element in the iterable, and then the function modifies, mutates that accumulator as you go through. The result of a fold is that accumulator, whatever you've changed. So it's a way of taking an iterable, and this is why its fold is sometimes called a reduce, reducing it down to that single value. If that seems really nutty, let's actually write a fold. We'll do a kind of contrived one, but we're gonna write a one that already exists, but we're gonna write it anyway. We'll call it add nums. So this is just gonna, well, Giant, don't go away, because we're gonna write a fold that's gonna be a little bit more practical than that verbal explanation. So add nums is this text big enough for y'all? If it's not, let me know, but getting it bigger, this is like cartoonishly large for me, so I'm hoping this is big enough. Okay, so add nums. So what we do with add nums, and this is how Haskell works, it's exactly like using map in, well, Neon, it's like using map in Python. Here's the crazy part. Map is actually a specific implementation of fold. Fold is the generic. So add nums is going to take an array of integers, or a list of integers is how we would describe it in Haskell, and returns a single integer. Okay? So it's the sum function, but we're going to write it ourselves. So add nums, we haven't gotten to the accumulator yet. We're just defining the function. We haven't gotten to the accumulator yet. So add nums equals, and here's where we start doing the thing. So we're going to say fold L, which is fold from the left. Okay? So fold L, just like our definition here, takes, and this is where we really want to start reading the function definition. So fold L has a requirement of foldable, whatever type T is. Okay. The first argument it takes inside these parentheses, this might look a little bit funky, but basically it takes a function that itself takes two arguments, B and A. B is the starting point, and A is the, oh, I'm sorry, B is the accumulator, and A is the element of the thing that we're iterating over. And it has to return a type the same as the accumulator. We'll see what that looks like in practice. Then, so that's the first thing it takes. Then it takes the accumulator, and then finally the argument that it takes is the thing that it's iterating over. And then what the whole thing returns is whatever that type B is. I know that Haskell notation can take some time to read, and because we're not dealing with any useful data types here, it doesn't super make any sense. If we were to specify this for our current thing that we're doing, let's actually put that in a comment here. We're saying that the function, the predicate, takes an accumulator, which is an integer, right? And then this also happens to be an integer, but it's from the list of integers, right? And then, my bad, this isn't going to be useful for us at all because it's going to be all ints. Let's just do it. So fold L. The first thing that it takes, we saw, was the predicate. And we saw that it takes two arguments, the accumulator and the element of the list. And this is how we write anonymous functions, what we call them, lambda functions in Haskell. So it takes two arguments, A for accumulator and X for the element. And, or actually, I'll say add nums ends, and we'll call it N to be a little bit clearer. This pluralization of a thing, like ends for numbers, is very common in Haskell. So we say it takes the accumulator and N, and we're just going to say A plus N. I know it's silly, but that's what we're doing. So that's the fold, or that's the predicate. The next thing it takes is the accumulator, so we're starting it at 0, and the thing that it takes is ends. Now I'm getting a blue here because Haskell's like, what are you doing? What are you doing? Because I've overwritten this. It's telling me I can omit some of this. I can make this a little bit cleaner in my writing, but I wanted to do this specifically to show you every piece of it. So let me load this up in GHCI so you can see it. So I'm going to load up GHCI, and I'm going to load the 01 file. Okay, and just to show you how this works, if I type main, see how it runs the main function from my file? Super cool. Okay, now I'm going to run add nums, and I'm going to give it, 1, 2, 3. And it gives me 6. So it works totally fine. That is how fold works. But if you start thinking about different kinds of problems, a lot of things, it turns out, are actually folds. In fact, Neon, you were talking about square nums, right? Let's like map. You were talking about map. Let's say we wanted to create a list of we just wanted to write a function that took a list of integers and returned another list of those numbers squared. What we would do, let's use that fold L again, except this time we're beginning with an empty list, and instead of A plus N, because the accumulator is not a single integer anymore, what we have to do is A plus plus N. Oh, hey, Joe. Man, I like Haskell. The trick with the plus plus operator is that it has to be inside of a list. That's not a noob question at all. So what the plus plus operator does is it combines it, or it really concatenates two lists. So you can see it down here in GHCI. If I do a list of 1, comma 2, and then plus plus 3, it'll fail on me. But if I do 1, 2, plus plus, and then another list, that's how I combine lists. It's like append, right? So that's how we do that here. So what we're doing is the accumulator is a list already. So I'm taking that individual number from ends and I'm wrapping it in a list here so that I can easily concatenate it. The problem is that what I'm doing is I'm actually n times n, right? Because I want to square the thing. Now this is a super overwrought. Let me reload. So if I do square nums and 1, 2, 3, I should get 149, right? Yeah, I can math. Now, this is like as explicit as you can write this, but it turns out that there are some shortcuts that you can take to writing this. For one, it's telling me why not get rid of the ends entirely, because you can actually imply the final argument. So I can just get rid of the ends entirely. And it'll still work because it knows that you're giving it this list of integers as the first argument. So that's part one, and we can do that up here as well. Now, add nums has another simplification. Haskell's telling us, hey, you goofus, you just wrote a whole lambda function to add two things. Just use the plus operator. And then even then it's like, hey, you just rewrote sum, so just do sum. It just takes the last declared variable for the final argument. That is correct, Neon. And that's a little bit squiffy, which is why I tend to write it explicitly, because this can be easy to miss. But in idiomatic Haskell, this is how you would do it. But the bigger point that I wanted to make is that fold is this magical generic. And if you're paying attention, this square nums that we did here, this would be, if we did it in Python, it would be like map lambda n times n against n's, right? It works very much the same way, but it turns out that map is actually a specific implementation of fold, where map is an implementation of fold in which the accumulator in a fold is a list. That's what map is. Servain, sorry, webinar. Well, thank you so much, and you're very, very welcome. You do not have to know a lot about hacking to be here. This is a pretty chill community. We're doing some programming tonight. We're actually not doing, we're doing hacking in the traditional sense of cobbling together code, but we are not going to be, compromising any systems or anything tonight. So yeah, no, regardless of your tech interest, you're welcome here. All right, so with these out of the way, let's actually get into the challenge. So the challenge here is we have this list of numbers. We have to determine whether each one in turn has increased or decreased. And we don't have for loops to make that happen. So how are we going to do it? This is where I really think the pseudocode and thinking through the data types that we're pulling is going to be helpful for us before we start writing our Haskell. Because ideally, your Haskell should be pretty clean if you've done everything right. So we know that we're going to be getting in a list of strings, just kind of like as a first step, because we're going to be reading in the file as an input, and then we'll have a list of the lines, right? Okay, so the first thing that we need to do is we need to turn that into... a list of integers, because we have to do mathematical comparison. So that's kind of like the first step. We have to turn each one of these into integers. Okay, no problem. Oh, I'm glad I got your name right. Yeah, and if I ever mispronounce somebody's name, please, provide a phonetic or, message me on the site or something. I always want to make sure that I get people's names right. And even if it's in a language, maybe especially if it's from a language that I don't speak, because it doesn't matter where you're from, you deserve the dignity of having your name pronounced correctly. All right, so after we have integers, what do we need next? Because remember what our goal is. This is also a cool thing when I'm thinking in Haskell. I'm thinking about very beginning and very end. So at the very, very end, I know that I want to get, I'll actually put that on the next line. I want to get to a single integer, right? And then I have to like check for increase. I don't know what this is going to look like yet, but there's some sort of implementation that I'm going to have to write. And then at which point I have my integer. And this thing is going to basically, if you think about what we were just talking about, doesn't this sound, look at this. We've got an integer, or a list of integers, and we're going to a single integer. Doesn't that sound kind of like a fold? Doesn't that sound like a fold? The only trick is fold might not be the most useful because we have a particular issue, which is that we need to check the previous value to do our decision making. And inside of that predicate for the fold, traditionally, we don't have access to that thing. And again, like in a for loop, you would use the index of the array or the list to do that. We don't really have that option. You can do it, but it's like ugly. So there's some other ways that we might think about doing this. I'm sensing this might be a recursive. There's like a cheap way to do it, but I don't want to do it that way. I want to do it the right way. The right way, the clean way. So let's go back to our scratch pad here. Let's talk about how we're going to get our input in. The one thing that people don't like so much about working in Haskell is the I/O, and I totally understand that. Which is, if you think about the way that these functions have been written so far, they are pure functions, right? There's no what are called side effects. And that is how Haskell expects your life to work. It doesn't accommodate the real world super well. It's a very pure, ivory towery language. And so when you have to do something messy like read from a file where there's no necessarily returned data type, or you have to run the program where there's no returned data type, it can get a little bit funky. And that's what this I/O is all about in this main function. In this main function, you have this I/O, which is, it's called a monad, and you may have heard that when people are complaining about Haskell. Don't freak out about that. Essentially, think of this as a way of handling side effects that aren't direct return types inside of Haskell operations. So that's what you're seeing here. With put_line, you can see that put_line returns this I/O type. It's how we make this match this type. And that's why we were able to run, if I run main here, right, it says hello advent of code. Okay? Well, I have some other stuff that I need to do if I want to load that file. So to show you how that works, we actually can create a block of I/O stuff with the do command. So do allows us to create a block of things that have I/O assignments. And the first one we're going to do is we'll say text. And I'm trying to assign a value to a variable here, but notice that the equal sign already has a special meaning in Haskell. I am not creating a function definition or a function implementation, so I can't use the equal sign here. It's not like, well, it's not like nim, where procs use the equal sign. And so does variable assignment. And it's not like F#, which does the same thing. No, no, no. We have to do something else. We have to use this operator, which is how we do IO-based assignment. So text this is where we're going to read the line. So we're going to read the file, and we're going to give it input.txt. Read file gives us an IO string. And the IO is this monad type, which itself contains the string. I know that's strange, but this assignment operator here is what handles that IO and gives text the string at the end of the day, if there is in fact a string to be pulled from that. All right, that's how we get text there. And in fact, because it's a string, I can replace the putStir line with txt here. And this will just work. Gingerroot, thank you so much for the gifted sub to Hennessy Dev. I really appreciate that, and I'm sure Hennessy Dev does too. Let's load up 01 again, and let's run main. This is going to print out 2,000 lines of text. But hey, it works. So we've gotten our first step, right? We've gotten our strings. Actually, we haven't. We have a string. If we were going to be more explicit about what's actually happening here, is we have a string. Now we have to turn it into a list of strings. Now you might think, okay, cool. Does Haskell have a lines function or something like that? It does. But there's a problem. And you can see how it works too. Oh, I would also make mention that in GHCI, you can do type, I think type, lines. Yeah. And :type will give you the function definition of any function in Haskell. So that's super handy. Now, lines is a string, which returns an array of strings, or a list of strings. And if I did lines 1, 2, it gives me just that, right? But if I separate those with a new line, it splits it up. So it's really, really, you know, elegant. It makes sense. But we have a problem. What's the problem? The problem is that, well, not a problem so much, but you might think, okay, cool. We'll say like LNS, we'll assign it this way. We'll say lines txt, because I just got that txt. But we can't do that because of this thing. This thing is expecting an IO. Right? It's expecting an IO, but unfortunately we're giving it not an IO string, we're giving it a straight string. So in fact, we actually have done all the input-output that we need to do until we do the putStir line. Instead, we need to use this inside of another kind of statement called a let statement. And so we'll say let, and then we'll do ends for our numbers equal lines txt, and unfortunately, so what that gives us ends then, you can see, that's a string. But if we wanted to turn a list of strings into a list of integers, how might we do that? So now we've gotten to here. We have a list of strings. How do we get to a list of integers? Well, the question you might ask is, does Haskell have a function to parse a string as an integer? And it does. Prelude to read, no parse. Read does work. We look that up, we'll see. Let's go back to good old Google. Right? So if we do, actually, we can give it the type if we want, manually. Read 7, int. Yep. Works great. So we can say if we had that and we have that map, because remember we do have a map. What happens if we map read against 7, 8, 9? We'll give it int again. What am I doing wrong? Let it read, no parse. This is illegal type. I won't worry about it in GHCI for the moment. I'll just do it in here, where we're gonna, if we, hold on a second, we map like +7, just to show a map here, 7, 8, 9. Map will take a function and apply it to an iterable. So that is what we're going to be doing here. So ends is not just lines, it's going to be map read lines text. Now, map what? Map read against lines text, but this lines txt is actually a combined statement, right? Notice that in Haskell, we don't really use parentheses to call functions. The arguments just come after the function name. So to separate these, we could wrap these in parens, and that stops yelling at us. But the other thing we could do, because parentheses are kind of not idiomatic Haskell, is we can use the $sign separator. And what the $sign separator means is essentially we're wrapping parentheses around the next arguments. So we're saying map read, and then the second argument to map is this whole thing. Okay, so ends is now, if we've done this correctly, an integer, or a list of integers. Or it will be once we tell Haskell what we're going to be doing with this thing. This is where we need to get to our actual implementation. Okay? Now, our result is just going to be 0. use print. Now, our result, we have to implement this, right? Whatever the thing is we're going to do to start counting up our increases. But now, it's going to yell at us. And it's going to yell at us because we're not actually doing anything yet. We'll say sum ends just to clean it up. So this sum, obviously, we need to replace this with whatever we want to do. But now let's load our Haskell file again. We'll call main. And it tells us what the sum is. Not too bad, right? But now we actually have to write a function that actually does what we want it to do. So we're going to get rid of this up here, and we're going to write our actual function. We'll call it increase check, or check increase. Increase count is better. We know that it takes in a list of integers, and we know that it returns a single integer. And we're going to give it a couple of, because I think the way that we want to do this, let's use our scratch pad for a second to think this through. So I've got my list of integers. Let's say, 1, 4, 7, or 6, 5, 6, 7, 9, 3. I don't really care. Okay, but I have that coming in. What I want to do is I want to split it between it and the rest of it. Like this. And I want to say, okay, So one thing that Haskell lets you do really easily is deconstruct lists into like its head and the tail, meaning the rest of it, like this. The problem is, for the first one, I actually need to guarantee that there's nothing back there, right? So instead of looking behind, if I'm always looking ahead, that might be something which I can do. Is it reverse? Yeah, reverse. If I flip the list, that might actually work a little bit better for me. So let me shorten this up just so it's easier. So we reverse it and we say 4, 3, 1. Okay. Now we're actually looking ahead to see if there's a decrease, right? Right. So now we're saying if the head is greater than the tail, now we know that it has happened. And if so, then we're going to say it's 1 plus, and then we're going to call it again. And we're going to call it with the remaining list. So we say, okay, then that means that it's we've counted 1, right? And then so 1 plus, and then the result of the list. Otherwise, if there was a decrease, it's 0 plus the rest of the list. And we continue through that until we get to the very end of the list, in which case we return 0 because there's no increase or decrease at that point. And then an empty list also, we return 0. So that's how we're going to do that recursion. That might seem a little bit funky, but you'll see how that goes. So we're going to write a couple of base cases here. So we're going to say increase count for an empty list equals 0. No increase counts whatsoever. Yes, I know that the pattern matches are inexhaustive. Thank you. Increase count of a single n is also going to be a 0. So an empty list or a single element list, we know that those are going to return 0s. Okay? Here comes the next part. Increase count of n and n's equals if n is greater than head ends. And head is kind of what we're already doing here, where we're splitting a list. But look at this. If we do, let me go back to GHCI. If I do head of 1, 2, 3, it gives me 1. Okay? So I'm taking that list again, but I'm just looking at that next element of it. So if greater head ends equals 1, then 1 plus, and then I love this, increase count ends. Else 0 plus increase count ends. It's recursion, exactly right. Although it's screaming at me now. Pattern's not matched. Hey, Grom. Well, slow boy, there might not just be boys here, just as a heads up. But we are working on some Haskell, and we're doing Advent of Code in Haskell. Don't worry, it's recorded, and if you saw the one at ShellCon, it was very much the same talk. Let me check my learn you a Haskell for great good stuff here. Make sure that I'm getting this right. Here we go. Oh. Duh. It's actually like this. There we go. Stopped yelling at me instantly after I turned that from a bracket to a paren. Hey, Slow Boy, there very may well be girls here, and even if we don't know it, we're going to be respectful anyway, so consider that your warning. So we have our recursion here, and in order for this to work, we need to give it some of the reverse ends, because that's how we're measuring it. At the end of the day, since we're getting the count, it doesn't really matter, but we just want to have that starting point of the end and then moving backwards, rather than having to try to like do a look behind to empty. Ah, good. My favorite question. Have you thought about using software and game development category instead? I have, and I'm not going to. Here's why. One, I don't really do software development. I'm doing programming kind of in service of the information security stuff that we do here. I'm not a game developer by any stretch of the imagination, and I don't want to get lost in there. The primary mission of this stream is more information security, so that's why we're in science and technology, until GoPro Sloyo's petition for a cybersecurity category is adopted, at which point I will change the category from science and technology to cybersecurity. So that's the deal there. All right, so are we done? Are we done? I think that might be it. Did I forget to save? Oh no, I forgot to use increase count. Is that right? 1581? Oh, yeah. So, thanks, Gingerroot. So, I don't know about you, but I think this is super elegant, where we have a recursive function to do what we otherwise would have been doing in a for loop, right? And we have our, whenever you're doing a recursive function, you want to know your base cases, right? Where do you stop calling the function? Hey, somebody else, it's going well so far. My comp sci knowledge seems to be on a solid foundation. Boy, that is a thin veneer, but thank you. What resources do I use to grasp all the concepts? Wow. You know, Giant, I have to tell you, I've been doing programming now for, over a decade. And so I can't list for you all the stuff that I've used over the course of my programming career, but I will say that reading, you know, some intro computer science courses that are free on the internet are worth taking, and understanding why you do what you do, especially from a programming perspective. Actually, that's how I would put it, is that, you know, I can't tell you operating system theory, right? I don't know a whole lot about operating system theory if we're talking about computer science. I don't know a whole lot about the architecture of memory. I know a little bit about CPU architecture because of reverse engineering and binary exploitation, but like, if that's what we're talking about computer science in the academic sense, it's not. Programming, though, let's specify programming. The reason why my programming skills look the way they do is because I treat it like a craft. Katrine90, thank you so much for the follow. I treat it like a craft, and I want to learn how people do it very, very well, and I want to understand why. It's very much the way that I approached writing as an English major and as a writer myself. I want to understand what are the best practices, what are the things that, why are the rules the way that they are, and when is it right to break the rules? Sometimes that's true too. That's why. You treat it like a craft, you always seek to improve it, you look at the examples of people who do it very well, and you ask questions about why it is that way. In terms of resources, I will point you to one of my favorites is Exorcism, just for programming, exorcism.io, or I guess it's exorcism.org now, which allows you to not only practice programming challenges, but see how other people solve the problem, and you can learn from how they do what they do. I think that's a great one. All right, let's go to part 2 here. You break the rules every time I write grammar and I don't get... Yeah, like that run-on sentence right there, right? No, I'm just playing. Toni Morrison said that you get to break the rules as a writer once you know them. And I truly believe in that. Thanks for hanging out, Giant. I really appreciate it. All right, what are we doing here? Considering every single measurement isn't as useful as you expected. There's just too much noise in the data. Instead, consider sums of a 3-measurement sliding window. Oh God! All right. Again, consider the above example. Start by comparing the first and second 3-measurement windows. The measurement in the first window are marked A, B, C. The same deal. We might want to think about reversing it. Oh, gross. 3 measurement. The measurements in the first window are marked A. The sum is fine. Their sum. The second window is marked B. Its sum is 618. The sum of measurements in the second window is larger than the first of the first. Your goal is to count the number of times the sum of measurements in this sliding window increases from the previous sum. Oh, I see. This actually might not be terrible in Haskell. Haskell has a couple of things that might actually make this cool. Depending. So this is A, then comes B, then comes C. Okay. All right. I'm with it. Let's change this up. Actually, we just copy everything. And we'll go into 02. Open that up. Oh, let's move. And by the way, GHCI has a CD capability, which I think is really cool because it will unload any files and allow you to load up anything else new. So that's handy. Now, what has changed in this case? In this case, we're still using input.txt, but we have to split it up a little bit differently. Arthur Savici, thank you so much for the follow. Now, in this case, we're still pulling in a string, and we're still going to turn it into a list of strings, and we are still going to turn that into a list of integers, but here's where it gets a little bit interesting. Basically, the rest of this doesn't change, but the way that they're doing this three value window and then summing it adds a step in here for us, where instead of having a list of integers that is pulled raw from the strings, we still have that, but then we're going to do a thing that makes windows that gives us a new list of integers. And that make windows is really kind of tricky in a cool way. The first thing is we have to chunk up our list into every 3 values, right? And I'm gonna check Google to see if there's something cool that does this. I think there might be. Yeah. Oh, not quite what I want. Not quite chunksy there. And split is really not quite what we want. Do we have take while? Yeah. Take while is gonna help. Take is cool. So one of the things that Haskell is lazy. So I can say take 10 from 0 to whatever. And basically I just said take 10 from an infinite list, and Haskell's like, all right, I don't care. I don't need to evaluate the rest of that list because I don't have any calculations that require it. So you can tell me to take from infinity. That's no problem for me. And so if I have a list of, now if I try to take 3 from a list of 1, it'll just chunk it. So actually, this is going to be easier than I thought. We're going to do a very similar recursion to what we did before. It's just that we're going to return sums of the windows. If you think about it, let's go back up here to our little scratch pad, right? Say 3, 6, 7. Fine. Let's give it a few more numbers since we know we're gonna be. Okay, so this is going to go into our function, and we're going to split it very much like what we did before. We're also going to do that reverse thing because it was really handy. For specifically, actually, I don't think it'll matter in this case. We'd have to flip the inequality, but otherwise, totally fine. Anyway, point is, we chunk it. And in this case, we're going to chunk 3. So we can't use head, really. We have to use a different way of chunking it up. But then we sum that value, whatever that is, and then we We sum that value, we add it to our accumulator, and then we pass the rest of the list. So we actually do tail and send the rest of that back around into the function and do the same thing again. That's going to generate our windows and allow us to do sums. Oh, wait a minute. Even easier. I just realized. So if I do a so if I have ends, right, and say take 3 from ends, ends still has everything, right? It's not it doesn't mutate the list. But now, if I do sum take 3 ends, I just do that for each one and then pass tail through. Oh yeah, that's super easy. Okay. I love it. So we're going to write another function in here called make windows. And it's going to take in a list of integers. And this returns a list of integers. And make windows empty list equals 0. Make windows n equals n. And then make windows ends equals. Notice that I didn't destructure the list this way, because I don't actually care about the head in this case. I only care about the tail. Oh, my bad. It actually doesn't return. This is wrong. Returns that. Okay, so now what we're going to do is say return take 3 from ends plus tail of ends. Except that not tail of ends. Make windows tail of ends. Oh, my bad. Because what we want to do is sum the take 3 right? Now, why is it yelling at me? Couldn't mask expected type int with actual type. The first argument of $sign takes 1 argument. but its type int has none. Oh, I like this. Some take 3 ends. Oh, it's the tail that's messing with me, right? So Windows. Yeah, that's right, because it's everything but the 0. All right, it doesn't like the $ operator there for the parentheses replacement, but it is fine with that. So all we have to do here is add make Windows. So just to walk this through, we are we're reversing our numbers to do the same kind of comparison that we did before. But we're sending it to make Windows to make our 3 window blocks. And then we're sending that result to our increase count the same way that we did before. And that looks pretty good to me. Anybody have any Haskell questions or other programming questions or questions about what we're actually doing right here? Is anybody totally lost? It's okay if so. I'll try to make you unlost. This value is slightly different. How many sums are larger than the previous sum? Well, that was 1620. Oh. That didn't quite work. Okay, so something in our reasoning here that didn't quite work. Let's clean this up a little bit here. I'm going to comment this out. Say Windows equals make Windows reverse ends. And I just want to see if this looks sane. And we're going to print Windows. I just want to print that out to see if it makes any sense. No, and it's too long. And I think that's because... Yeah, that was dumb. It's summing those up. What's summing them up, but basically what's happening here is... Okay, so round one is... These get summed together, right? So in our new list, we're summing that... So what? That's 17. And then we're combining that with this list here. So we're combining that with this. The problem, then, of course, is that okay, so then in the next round through, taking 3 from this, and summing that. Oh, wait. I think it's the notation that's the problem. Oh, let ends equals take 10, 0, 10. Yeah, see, that doesn't work. But that works. I maintain that this is the way that you're supposed to do it, but it's annoyed at this here. But that's okay. I will use parentheses first and then see if we can clean it up. Okay, it doesn't need those parentheses. Fine. Now, what are you yelling at me? Couldn't match expected type int with actual type. Oh, right. Now, I maintain that I'm doing something different here, but we'll see. Nope, those numbers look the same. Oh, Gingerroot, you're absolutely right. So Does take 3 return less than 3 ints if that's what's available? Yes, it does. If I do take 3 of 3, 4, it returns 3, 4. So did I misread that? Are we saying if there's... it can only be 3? Oh, interesting. That's really important. So, second paragraph, last sentence. Stop. Yeah, thank you. Stop when there aren't enough measurements left to create any 3 measurement sum. Okay. Well, then. Then what we have to do is use a guard clause. I know I'm doing this wrong. I always forget the guard clause. Yeah, no, I'm doing it right. Yeah. So this is a cool Haskell syntax called a guard clause. And it has case of as well. But I like the guard clause, and this is why. So I can say it's like a conditional statement, but I think it's a little bit cleaner, where I have a full implementation of the function based on the condition of my argument. That's when you would use a guard clause, basically, is when it's conditional on the state of the argument that isn't clearly defined by these other cases. I don't know if that makes sense. But yeah, okay. Good catch, Gingerroot. Thanks, bud. Still getting 1618. Oh, wait. That's a different number than we got before, right? We got 1620 before. Was it that close? I guess it would be basically off by 1 set. Ha 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 ha. That feels great. I usually don't do these challenges because I don't like math problems. Ginger, tell me what you think about the way that these solutions look compared to what you were doing in Python, because I know you were doing these in Python.
Experiencing right now is called true envy.
You're about to experience my heel in your manhole if you don't get on the phones now. And please try to dress like losers who work here. Thanks.
I thought you looked cool. We look very solid.
Logic's pretty much the same. Yeah. There's just something I find very elegant about the Haskell syntax once you understand what you're doing in it. I like the way the code looks. That's a very, it's almost an aesthetic thing, but I also like the way that it forces me to think about my code before I start just banging away at for loops. That's another part of it for me. I like that it makes me do this. Thinking about your code, right? I'm setting up the plan. It's like plan the code, then code the plan, basically. And I like that it makes me do that. All right, we'll try number 3. We are going to change up the music, though, because that's enough of that. Oops. It's too easy to just start typing without thinking the whole problem through. Yeah, except here's the thing. It's actually not that... Whoa. It's not that easy to do in Haskell. You actually have to plan this out. Oh my. A submarine has been making some odd creaking noises, so you ask it to produce a diagnostic report. The diagnostic report consists of a list of binary numbers, which, when decoded properly, can tell you many useful things about the conditions of the submarine. The first parameter to check is the power consumption. You need to use the binary numbers in the diagnostic to generate 2 new binary numbers called the gamma rate and the epsilon rate. The power consumption can then be found by multiplying the gamma rate by the epsilon rate. Each bit in the gamma rate can be determined by finding the most common bit in the corresponding positions of all the numbers. Boo. Considering on the first bit of each number, there are 5 0 bits and 7 1 bits. Since the most common bit is 1, the first bit of the gamma rate is 1. So the most common is the bit sequence by position. Okay. The most common second bit of the numbers in the diagnostic report, 0. So, okay. Got it. The epsilon rate is calculated a similar way. Rather than use the most common bit, the least common bit. Since it's binary, it wouldn't just be common or uncommon, not least common. So the epsilon rate is 9 decimal. Multiplying the gamma rate by the epsilon rate produces the power consumption. All right. I think I have a handle on this. I don't love it, but okay. Let's get our puzzle input. Oh boy. Okay. Save that. And I'm just going to copy the main function over here so I don't have to rewrite that. Make sure we're all good here. So one thing I know that I'm going to have to look up, because I have never had to do this, is binary in Haskell. Dealing with binary data. Thank you. Oh no, this is like dealing with bytes, like binary blobs. That's not actually what I wanted to do. Binary numbers in Haskell. I wonder if it's in there. This was 2015. Maybe they just added it. Nope. Oh, neat. Well, that's not too hard. So do I put that up at the top here? Cool. Neat. That was a lot easier than I thought it was going to be. That's handy. Well, maybe. No, I didn't. Perhaps I intended to use data kinds. Read no parse. I'm gonna look that up. Haskell. Make sure I get this right. one couldn't possibly return an int. Oh, do I put it... Hold on a second. That works. Ooh, it has no idea what to do with that. So that's going to be a little bit tricky. Oh, read bin. Cool. Oh, snap. What's up, Tiberius and friends? Very nice to see you. We're doing some Advent of Code, and we're doing it in everybody's favorite language, Haskell. Oh no, what did you do, Haskell? You know what? Stow the Haskell hate. I'm not here for it. Haskell, it's a bad rap. Look at how elegant these solutions look from the first two challenges. They are beautiful. So, thank you for the gift, Suborbital. Tiberius can afford his own, but you're very generous. Headringer, thank you for the follow. I do appreciate an elegant syntax, it's true. Okay, so we may not need binary literals, but let's just get the basics out. Let's just make sure we can read the text file in, and we'll put strline txt just to make sure that everything looks good there. And let's get our GHCI up and running. Wonderful. Okay, so our text file is connected. We're able to read that in. And so the problem as stated for number 3 is we're reading in these strings, and we actually want them as strings at first, because we're going to be evaluating their positions. This is interesting. This is again where planning before we start just jumping into code is important. Let's get our scratch pad up. So once again, we know that we're starting with a list of strings. And by the way, in Haskell, a string is actually already a list of the car type. Very similar to, C actually, right? And Rust as well. That this, at least the stir, there's a car that's underlying the string, and that's important to note here. And it'll matter for this because we are going to evaluate the positions of the strings. Now, are all of them the same size? They are indeed. They are all 12 characters long. Okay. So that's handy information. We may take advantage of that. So they're all 12 characters long. And so for each one, we need to determine the prevalence of, or the number of times a 0 or a 1 occurs, if that makes sense. And so what we're really trying to come up with here is a list of integers, right? For prevalence. Like this, right? Whatever the count is, and the ones like so. By position. Now, we have so far avoided trying to do indexing of lists, but it's not impossible in Haskell. The double bang operator allows us to access individual elements within a list, and I think that may be what we're going to do here. Just given the way that we're looking to do this. So we need to determine the prevalence of the zeros and the ones. And this is where we're trying to think about the pure function flow, right? It's not like we have global variables that we can mess with. I think Haskell has a couple of built-ins that might be helpful to us. Let me just see. Count. MacGyver, thank you so much for the follow. Now, can we index strings? Oh, we can indeed. So, hey, Sar. So what we can do is in something like this, we can split it up. And in fact, I mean, the problem is that's already split. It is already cars. There's no it's already essentially a list of cars. I don't need to split it again. Doing well, although I may have bitten off more than I can chew with this last challenge. For right now. It's not a matter of solving it, it's whether I can solve it interestingly on stream. But, let's see how we're going to do here. We need to evaluate every position in each string, and we need to store it somewhere. All right, I'm getting a little ahead of myself. I'm feeling myself get, like, all the way to the end of the problem. Like, oh my god, how are we going to do this? So whenever I feel like I'm getting to that point, the strategy is take the big problem and break it down into a smaller, more solvable problem. So let's do that. The first problem we can attempt to solve is, how do we determine the number of zeros and ones in this thing? To do that, God, do I have to... Zip might be helpful for us here. I'm just trying to think. Because you can create these tuples, right? Wait a minute. The only time we actually need to do, I was just thinking ahead, the only time we actually need to evaluate a binary number is at the very end. When we're multiplying the gamma and epsilon factors, right? We don't actually have to translate these input numbers into binary. We just need their zeros and ones. That's interesting. Okay. All right, let's make a bin count. It takes in a string and gives us back a count of ooh. It's not really what I want. A count of zeros and ones. I don't really want that. Because I don't want the sum total, I want them positionally. Okay, what is the same size? The same size as a result is... Let's go back to our scratch pad here. I'm sorry that it's like hard to... This is probably not the most interesting stuff, just watching me think this through, but... So we've got a list of strings coming in. We know that at the very end of our process, we want a... Well, we want an integer, which is going to be the multiplication. The epsilon and gamma. But before we get there, we need... Actually, kind of seems like we need a tuple. But of the epsilon and gamma. right? And how do we get that? Because in order to get that tuple of the epsilon and gamma, the epsilon value is the binary number that is from the most common digit per position. Okay, so what we might want to do is actually split. I've been thinking by rows, but actually, what if we split by columns? This kind of opens up a little bit. If we do column digits, and this takes a list of strings, and it's going to return a tuple of integers, numbers of zeros and number of ones. Ooh, I like this. Okay. And it's also going to take, by the way, an integer for column. Yes, 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 yes. So what we're going to do, let's look at our input. Wrong thing. What we're going to do is we're going to give the column digits this whole thing, but we're going to give it a column number. And it's going to take that value from each of the strings and count and modify our tuple until we get to our final. Ooh, I like it. I like it a lot. Okay. So, this is going to be a fold, interestingly. Column digits. We're going to name these, right? So ends and col equals. And we'll say we're going to write a couple of helper functions here. Or, sorry. That's not how we do it. My bad. My bad, my bad. We're going to do bold L, and we're going to do the accumulator and the specific number. If is 0, n call. Wait, is 0 exists already? Oh, Haskell. Wait, does it really? No, okay. It's just being cool about it. And actually, we're going to destructure our tuple because it's going to be like this. ZO for zeros and ones. So if is 0, then z plus 1 0, else z o plus 1. And we... God, that's long. We give it an accumulator of 0, 0, and we give it the ends as the thing that we're walking through. Oh, doofus. There we go. Now, this is 0 is a problem because it doesn't exist yet, right? Where is 0? Just bool, right? Like, literally that. Okay. So, cool. What this produces for us... I know it's long. I know it's so stupid long, this line. But we're saying, for whatever column, if it's 0, then we return, we add 1 to our 0 part of the tuple. Otherwise, we add 1. So we're, for each column, then, we can produce a tuple of 0s and 1s. Yeah. Okay, so let's give that a shot. What we're going to do, so text is the read file. Then we're going to say let binaries, I'm being a little bit more explicit, equal map read no. Actually, just lines from txt is all we need there. And then we're going to say call counts equals we'll just do it for 1 first. We'll do column digits against binaries 0. And then we're going to print the call counts. We're just going to do that much to see what happens. $521 and $479. So now we just have to do that across each character. So to do that, These aren't inclusive, are they? Oh, they are. Does that work? Okay. We now have our column counts. And so now we can do this in inline, but I'm gonna do this as a simple function. So we're gonna make gamma. I'm not really from the Midwest. I'm from Philly, but I've got to be careful to not say gamma. So if I remember correctly, we don't have to remember. I can just look. The gamma rate is the most common value. So I just want to make sure I'm doing this right. What is it, dot zero? Can't you're right, I can't add to a tuple. Retrieving values. Oh, FST. And SND. Okay, so great. That's how we do that. Okay, so gamma will return a for the moment, let's make it return a string, because we haven't messed with the binary stuff yet, but for call counts is so again, we're taking a list of tuples, but a list, and we're reducing it down to a single thing. This is where a fold comes in handy. So we're gonna do a fold, and the fold is gonna do so our accumulator is going to be We'll call it G. And we'll destructure our tuple to Z and O again. And we'll say if Z is greater than 0, then we'll say G plus 0, else G plus 1. What is this dark art? This is Haskell. We're folding it against an empty string, and we're folding it against C's. Oh, I forgot the word then. Then. And it's going to say, hey, you're doing this harder than it needs to be. 0 if Z is, why not? Oh, it's just trying to say I don't actually have to use C's here because I can omit the last character. That is true. I can do that if I want. Or the last argument, I should say. That's a kind of a weird Haskell-y thing where if you're doing a fold or some other argument that accepts an X number of arguments and you're explicitly defining the argument here in the function definition, you can just omit it. And Haskell's like, okay, I got you. I'll toss that in at the end as the argument. Kind of annoying, but it does work. This makes the gamma, right? Because it's the most common. Similarly, we can make the epsilon. And literally all we need to do is flip this. Oh, no. It's not Z greater than 0, Z greater than O. Whew. That was almost a really dumb mistake. But now we're not accounting for the possibility that there's a tie in the commonalities. Which is interesting. I would have thought they'd have something about that, but regardless, we've got epsilon here. And let's see what this does. Now, looking at it, I'm recognizing that, of course, they're inverted, right? One is the negation of the other. But whatever. I could literally have just bit flipped one of them. But that's okay. Now we have to turn these into binary numbers. And for that, Fold right. Oh. I like this a whole lot. That's a nice little snippet. I don't mind doing a little Stack Overflow for that. I don't actually think I need... I don't think I need this. I don't think I need either of these. Why did it do that? Okay, now let's put that little bin to decimal. I like this a lot. Okay. So we're going to do... Actually, I'm going to print those again just to see it happen. I did not expect that to be right. I really didn't. What a good note to end on. So, what did we do? The first thing we did was we imported our input text file. We pulled out the column counts, which I think was a good way to do it. And we simply created a tuple of zeros and ones by column. And we mapped that against just the range of the length of the digits. Pretty easy. And then we created the gamma by looking at the most common, right? If the 0 was greater than, then we did 0, otherwise 1. Now, I should mention that because they were inverted, I could have done something crazy like do a negation, right? I could have just done like a simple lambda function to say for like map, if it's 0, then give me a 1, otherwise give me a 0 or something like that. But, you know, we have two explicit functions here using a beautiful fold. Do you see, like, I think that's tonight's thesis. Do you see the power of the fold? Once you understand when to apply it, it makes so many things easy because it's this general problem type. And after that, we'd use this little, admittedly, Stack Overflow kludge, but super handy, just to convert the binary string to a decimal. And it itself is doing a fold. Notice that it's using a right fold, though, rather than a left, which makes sense because we're doing values from the beginning of the number, right? From the zeros, ones column to the twos columns to the 4. And it's basically, there's our accumulator, there's the string, and we're doing the string, or the S times 2 plus C, 0. And we're mapping, reversing it, and then we're mapping it C2I, where C2I. then 0 else 1. Right, the character 2. The character 2. Now, the dot we haven't seen, but the dot is kind of like a back arrow in a way. So we're basically saying map C2I becomes, this is ordered back in this direction. And ordered back to all this becomes then the argument, the final argument that we send to our fold R. Very cool. All right. Well, friends, I think that's going to do it for tonight. We did 3 Advent of Code challenges in Haskell, which is more than I thought we were going to do tonight. And I had a lot of fun doing them. I hope you did as well. So we are going to say goodnight. And let's see. Is Kay actually streaming? Yes, but we did them last night. So let's this is Z Quaker. What's Z Quaker up to? I don't know. Oh, they're in Espanol anyway. Ocean's Giant is streaming. That would be a cool one. All right. So actually, they're just doing a game. So I think we're going to just call it a night. So friends, have a good night. I'll be back on Saturday doing blue team stuff. But until then, be good to yourselves. Be good to each other. And I will see you next time. Happy hacking, everybody.